Virtually every modern computer relies on an architectural model conceived in 1945 by John von Neumann. He introduced the stored program concept, the design choice to place both the data and the instructions to process that data into the exact same memory space. This model separates the computer into three physical pillars: the central processing unit, main memory, and input-output units. By decoupling the processing engine from the data storage, computers stopped being fixed-function calculators and became flexible, general-purpose machines. Isolated components communicate via a shared physical pathway called a system bus. The bus divides into three distinct lines. The data bus moves cargo, the address bus identifies the destination, and the control bus acts as traffic signals. Because all instructions must travel these shared lines, a system's overall performance is gated directly by the bandwidth of this interconnection structure. This pyramid illustrates how systems balance speed, capacity, and cost through a memory hierarchy. The peak represents ultra-fast, expensive internal memory like registers and cache, while the base relies on larger, slower external storage like RAM and magnetic disks. This reveals the von Neumann bottleneck. The CPU processes data much faster than it can fetch it across the single, shared path from memory. Modern hardware engineering relies heavily on placing strategic, high-speed caches close to the processor to mitigate this restriction. Looking inside the CPU, this schematic shows it as an assembly of parts: a control unit, an arithmetic logic unit, and temporary storage called registers. These components operate on a continuous heartbeat to translate code into action, a process called the fetch-execute cycle. During the fetch phase, the program counter identifies the next instruction's address and pulls it from main memory into the instruction register. During the execute phase, the control unit decodes that instruction, the ALU performs the required math or logic, and the result is stored. Writing efficient software requires mapping code to this physical cycle. Developers who minimize main memory fetches allow hardware to run at its maximum raw power.